Can everyone hear me okay? All right, let's get started. Pressing start. So I'm going to be talking today about a little bit more of an applied piece of work surrounding mobile robots and their use within retirement homes. My name is Kyle Booth. This is actually part of the journal presentation track based on a journal paper in IEEE Intelligent Systems. So basically I want to motivate this work through two things. The first is the rise of mobile robotics. If the conference schedule is of any indication, robots are starting to be used in different areas of practice. So a couple areas here, we have healthcare, order fulfillment, so like Amazon uses mobile robotics, emergency response, agriculture, etc. So robots are starting to be used in real-world applications. The second trend that I want to identify is essentially the progressive aging of populations worldwide. As time goes on, there are more elderly people out there. If you look at the y-axis, we essentially have the share of total population. The x-axis bins by age, and we can see that, again, over time, the percent of the elderly population is increasing. So it seems relatively straightforward that we might want to study mobile robotics for elderly care. One of the things that the elderly care community sees is they have a hard time retaining employees. So people start working in elderly care facilities and then they leave. They have very high turnover. So why don't we try to design and develop some sort of mobile robot assistant that can autonomously facilitate various things. In this particular work, we focus on activities. One such activity could be a telepresence task, where a robot navigates to a person's room, pops up a Skype chat, grandma's on the call or something like this, and has an interaction with the user. So this is one of the activities that we consider in this work, but there are other activities as well. And so the primary question becomes, this is a mobile robotic problem. It's HRI, so human-robot interaction. Is it actually possible to do this in practice? Sounds nice on paper. Can we do it in practice? This is part of the larger project that we have going on at the University of Toronto. And essentially this is assistive robotics for long-term care. Now this problem again is quite large. It has a number of components to it. You have lower level components such as path planning, multi-robot communication. You also have some higher level components such as gesture recognition. You might want to be able to tell if a user puts their hand up, that kind of stuff. And the two things that we're going to study in this work are the integration of multi-robot task allocation and scheduling with person search and identification. And this was essentially motivated by the fact that, sure, I can create a schedule that has a robot travel through the facility and facilitate various activities, but if I can't actually find the users within the environment, if I can't navigate to a room and find a user, then my system isn't very useful at all, is it? And so, again, task allocation and scheduling primarily concerns what tasks do we do, with who, where and when, and then person search and identification is a HRI, so human-robot interaction, and it revolves around how do we identify and find a user. So the problem at a high level, we're given a retirement home facility, we have a fleet of robots, we have a number of tasks that we can conduct via those robots, and we have a set of users. The tasks that we consider in this work are the telepresence tasks that I mentioned previously. We have bingo games that the robot hosts with multiple users, and the robot also needs to worry about its energy levels, visit recharging stations, etc. What we want to do is we want to generate and execute this guy, which is essentially a task schedule. So you'll note we have 4 users in this schedule with 2 mobile robots as part of our fleet. The robots are going to travel around to users' personal rooms or the games room. They're going to facilitate various activities. They're going to recharge when they need to, and that's kind of going to be how that works. So again, it sounds nice, but what are some of the challenges that we're trying to solve with this architectural work? The first is that at the start of the day, we have a robot fleet that has no indication of where the users are going to be for the rest of the day, when they're going to be available, and what type of activities they want to participate in. So at the start of the morning, we're going to send the robot fleet out, and they're going to try and find users and get this information. The second thing is, okay, now that we've received that information as parameters, how do we actually go about scheduling tasks and activities with the users? And then the final component essentially is, okay, we have a nice schedule now. How do we execute? So there's a bunch of challenging HRIs going on. How do we find a user in the environment? And how do we choose to interact with a particular user given that they might actually be in a cluster of other people, right? They might be in a group. So the solution framework that we leverage in this work is at the beginning of the day, we do user availability canvassing, again, so we send the robot fleet out in the retirement facility and get all this information about their personal schedules. We do activity scheduling, so based on those parameters, we create an activity schedule, and then we execute that activity schedule. On the right, we can see we have an animated image of the robot we have at the University of Toronto that actually facilitates bingo games. So we use grad students instead of retirement home users, but that's okay. And essentially, if I look at this problem, there's two modules within our project architecture that we're focused on integrating in this work. And the first is a robot person search module, and the second is a task allocation and scheduling module. So our contribution, this is kind of the detailed version of the contribution. We contribute what we call a multi-robot task planning and execution architecture. The robot person search module, as I discussed before, leverages work that was done at PlanRob 2016. And essentially this looks at, if I go to an agreed upon time and place, how do I actually find the user within that room? Or at the beginning of the day, how do I find users in general, given they could be in different rooms? And we use a routing dynamic programming method for that. And then we combine this with task allocation and scheduling software that leverages constraint programming. And so again, we're trying to solve what activities with who and when. At a high level, we implement and then we actually test this architecture on our fleet of real robots at the University of Toronto. Again, we're combining these two modules, and the combined architecture looks something like this. Which might be familiar to some people in mobile robotics. And this whole architecture is implemented on the robot operating system, ROS, which is an open source framework for implementing this kind of stuff. So just to give you a bit of an overview, the primary components of our architecture, it is centralized. And so we have a centralized server, a main component. And to note, the centralized server can actually reside on one of the robots in the fleet, kind of like the master robot. And then we have a number of robot controllers that are actually located on each of the robots within the fleet. And so the server and the controllers communicate via these dotted lines in the middle of the two architecture components. So to start with a centralized server, it's responsible for more global reasoning about the robot fleet, kind of more strategic level thinking. It stores information about the world state, as well as does things like execution monitoring. And then so this is actually, if you look at that block there, that's actually where the CP model is embedded, so it sits on that server. And when we look at the robot level controllers, we do local level reasoning here, actuation, sensing, and then these are where also the activity facilitation modules reside. And so we can see here that we have a local robot person search module that's responsible for doing that user search and identification. So first I'm going to explain some details about robot person search. So the purpose is to find users within the long-term care facility or retirement home. So we have a global version of it. So at the beginning of the day, it tries to find as many users as it can across the entire environment, does an intelligent room-by-room search. And then we also have a local version where if we're meeting a person at an agreed-upon time and place, the robot will navigate to that location and try and find the user there. So if we look at the global variant, the inputs essentially are going to be the regions within the facility, and then we also have user activity patterns that we've amassed as of historical data, and the output is going to be a search plan over the regions. The particular technique that we use here, so we model multi-region search as a traveling thief problem, and then we solve it with dynamic programming. And as you can see in the top right, we've taken, that's actually our floor plan at the University of Toronto, discretized it into a number of rooms, and then the fleet of robots essentially conduct a search for users over this landscape, trying to find as many users as they can in the allotted time, canvassing them for their availabilities, etc., such that we can plan the rest of the day. On the local level, we take as input our specific region, as well as the user or users that we're looking for, and then we're going to output essentially whether that user was found or not. The technique we use here is we take that individual room, and then we divide the region into cells, and we construct a tour of the cells. So essentially, after it goes into a cell, it looks for a silhouette. Once it finds a silhouette, it does facial recognition on the user and tries to ensure that that facial profile matches the one that it's actually looking for. Okay, so we talk about the task allocation and scheduling module now. So our inputs here, again, are our user availability and preferences that we received from doing our availability canvassing. We also have the facility floor plan, we have our set of robots and our set of activities, and the output is essentially the robot and user schedules. It's important to note that this is an NP-hard problem. It's essentially a multi-vehicle routing problem with a lot of very problem-specific side constraints. And again, we use constraint programming to solve this based on work that was presented at CP 2016. So just to talk a little bit more about that module, again, we start from that module, we model and solve the problem in constraint programming. Again, that's all embedded within the server part of the system. And then we produce and communicate that schedule to the robot fleet. So I'll give you just some brief highlights on the model itself. So trying to simplify things and group them together into constraint families. So we're trying to maximize an objective function. In our objective function, we try to maximize the actual amount of activities being hosted within the facility, subject to a number of families of constraints. So we have task sequencing and synchronization. Essentially here we ensure that user schedules and robot schedules are synchronized in time, task presence and precedence constraints. So we have these things called bingo game reminders. So the robots actually have to remind the users that they're in a bingo game about an hour before the bingo game starts. So there's some nice precedence there. And then we also have constraints pertaining to robot energy. If I unfold these a little bit, so our objective function, again, we're trying to maximize the amount of bingo played, subject to some sort of tie-breaking scheme on energy requirements, right? So we prefer schedules that have robots visiting the recharging station less often as a proxy for kind of minimizing the amount of energy used. If we get into task sequencing, you can see that if you're a CP person, you'll notice these no overlap constraints. So we've imposed those on both user and robot schedules. And then we also have a synchronization component between those schedules for the tasks that are supposed to involve people and robots. And if you're interested in the full model, all the details for that are available within the CP 2016 paper. So I won't go into any more detail there. As far as our experiments go, because we're doing these on real robots, we basically construct 3 mock scenarios at the University of Toronto of varying sizes. And so we limit ourselves to 3 robots because that's all we have at the university in terms of mobile robotics. So the 2 robots on the right are capable of doing telepresence operations. The robot in the middle can facilitate full bingo games. And so that's kind of what we're working with in terms of mobile robots. We also kind of allow ourselves a maximum of 15 regions, and again, this is that's a map of the actual floor plan we have at the university. So we're kind of implementing a mock retirement home scenario here, and again, using grad students as retirement home users. So just to recap, to help us kind of guide us through the experimentation, we're doing user availability canvassing, which involves global robot person search, then activity scheduling, which involves constraint programming, and then we have schedule execution, which essentially involves this routing plus local robot person search element. So if we focus first on global robot person search, again, need to find canvas users, generate the search plan, navigate to the regions, and then identify users. So the first experimental set looks something like this. So the first 4 rows of experiments actually pertain to generating that search plan of rooms. It says planner runtime, but I will note this isn't a classical planner in the sense. It's actually a heuristic method. That's why the runtimes don't actually change that much as the scenario gets larger. But we can see that plan execution, as the scenario gets larger, plan execution actually going out and finding users is taking longer. And so if we go down to the actual, getting in front of a user, identifying them, we can see that we have really good success rates until we actually get to user identification, where the success rates start to drop off a little bit. And this is because the robots can be very picky about if the user is slightly turned, it can't properly identify their face, and these sorts of things. So if we go on to the other side of this, where we have task scheduling and allocation, again, generate that activity schedule. And then we want to execute that schedule by navigating to the agreed upon time and place, finding the user, and then facilitating the actual activity, whether it be a bingo game or a telepresence task. And so again, the results for this, we can see Because we're modeling this with CP, which is a complete technique trying to solve an NP-hard problem, our runtimes start to explode fairly quickly. If we had larger problem instances, the runtimes would be quite a bit longer. We can see that the search tree branches start to get out of control as well. I will note that that first schedule that we're finding, we are solving it to prove an optimality within CP. And then again, I'll remind you, once we produce that schedule, we have to use the local robot person search to actually navigate to and find users. And again, we're seeing high success values, except for when we get to user identification, where it can be quite difficult to properly identify faces. So that's more or less, I want to conclude with that. So one of the things I want to leave you with here is that actually integrating planning and scheduling research onto real robot architectures, I think, is a really important problem. And it's also very challenging, especially when we're dealing with human users that are moving inside an environment. So I would urge you to take, your gazebo simulation experiments and try to embed them on real robots if you have the opportunity to do so. In this work, we've successfully integrated, again, the person search component with the task allocation and scheduling component. And then in future work, we want to improve essentially our ability to respond to higher levels of uncertainty. So say we do misidentify a user, we want to be able to recover from that. If the robot completely runs out of energy, we want to be able to recover from that. That sort of stuff. And with that, my presentation is complete. Thank you very much.
Thank you. In find users, you use facial recognition, right?
Pardon
me? In the find users.
Find users, yeah.
Yeah, you use facial recognition.
Yes, we do.
Okay, if somebody like me shaved his beard.
Yeah, chances are it might actually have an issue with that. So.
So what you can.
So I mean, the easy
did you
solution
try
is don't
fuzzy
shave,
logic?
Right? Yeah, no, so that, again, that's as part of future work. So that module for facial recognition is actually, it's part of another student's work that we're leveraging. But yeah, as you can see, the failure rate was the highest there. And so that's obviously a place that we can improve on going forward.
Thank you.
Yeah.
I've seen, nice work by the way, I've seen there is not 100% success rate also for the navigation part. What were the root cause of failures there?
Yeah, so for navigation, if I remember correctly, we're largely using the move base as it's native to ROS. And it does have some particular issues with doorways. So you might have a doorway, and it might have some sort of paneling along the bottom that the robot gets caught on, and then some of the wheels still move, and then all of a sudden the robot isn't localizing properly, that kind of stuff. So I would say the improvement there isn't necessarily that the robot didn't receive the right navigation command. It's just some sort of physical issue with the actual robot getting from point A to point B.
Thank you. I found very interesting well, so let me ask, for those of us who do work with real robots, uncertainty is huge. And what I didn't hear you talk about, which I'd really like to hear a little more about, is in your scheduling, how do you take that uncertainty into account? So for instance, it may take much longer, much shorter for you to find a person than you had anticipated.
Yep.
And how is that flexibility built into the schedule, and how does the schedule get updated when monitoring tells you that you're not working according to schedule?
Yeah, so that's a great question. So the architecture as posed does support doing rescheduling, replanning. The rescheduling that we do right now is extremely naive. There are situations where we enter a rescheduling instance and the remainder of the problem is actually infeasible because you've kind of worked your way into a corner. And as I mentioned on the final slides, that's actually kind of future work for us. But when it comes to producing that activity schedule and then trying to actually absorb some of that search time that goes on inside the person's room, what you can do that was kind of done is a quick and dirty. You can just extend the duration of the task. and then schedule the extended version of that task, assuming you won't end up searching for some sort of obscenely long time. But this is a great question, and as I said on the last slide, dealing with that inherent uncertainty is something that I'm going to be looking at going forward. So, and I've seen some pretty nice talks here at the conference that have given me some ideas about that.